we're going to do a review lecture on kinetics. So you need to have a calculator and a pencil. So if this was, I'm going to do a couple little like small review things, and then you're going to try a problem. I'm going to do a little bit of review, and then you're going to try a problem with it. So your entire exam is all kinetics. And so again, what is kinetics? It just describes the speed of the chemical reaction and the factors that affect it. And then we also can determine the mechanism at the molecular level. So those are kind of our big things that we're going to be doing with kinetics. And my screen is not working. So we also talked about collision theory. And remember, collision theory talks about how the molecules have to collide to react. They have to have enough energy, and they have to have the correct orientation, right? So they have to hit with both enough energy and the correct orientation. And so I actually have a cool little thing. So here we have two molecules and they want to react. If they don't have enough energy, nothing happens. They also, if they are not in the correct orientation, nothing happens. Even if they have enough energy, they have to have both the correct orientation and enough energy to form the product molecules. And that's collision theory in a cool little thing. All right, so here is our reaction. Here's our rate. So remember, this is the rate law. So the rate law is always rate equals K times the concentration according to reactants raised to some order. Now this order here, this 2, is always going to be determined experimentally, right? So this rate law, you cannot tell by looking at an equation here unless it is an elementary equation. And the elementary equations are the one we do when we're doing the mechanisms, which we will get to. So this is a second order reaction, and how we say that is we say it's second order with respect to NO2. Here's another reaction. We're actually going to prove the mechanism to this reaction today. This rate is first order with respect to H2 and I2. So we would say it's first order with respect to H2, first order with respect to I2, but overall, it's a second order reaction. So second order overall. So that's how we read our rate laws. So, and this is going to be important, for example, when you're taking your exam and your final, this is going to help you make sure you understand what the questions are asking, right? And so rate laws are always determined experimentally. Okay. So here is your first problem. I want you to write the rate law for the reaction, and this is N2 plus O2 goes to 2NO using this data, and determine the overall rate law and the value of the rate constant. This is exactly what we're doing. We did it for your pre-lab, like to the T, we did this for your pre-lab for experiment 10, and this is the first part of your lab for experiment 10. Okay, so try this. And then type your answers in the chat. Go as far as you can with this. And then we're going to go over this together. So I'm going to give you a few minutes to work on this. It's a long question. So you need to figure out the overall order of the reactions, which means you need to figure out the order with respect to both N2 and O2. And then you're going to write the rate law and then find your K, which is your rate constant. So try this and we'll go over it in just a couple minutes. Okay, so I'm seeing a few of them. Do you need another minute or two, or are we good? Another minute? Okay, all right, I'll give you another minute. Okay, so I'm seeing a couple different answers on here. So this again is just like we did in our pre-lab. So if you want to review the pre-lab video, I go through this in great detail. So again, the pre-lab for experiment 10, I go through this specific question just like this in great detail. Also, this is the second lecture. So if you're having trouble with this question, it's the second kinetics lecture where we spend the entire lecture going over questions exactly like this. So that's where you should go if you're having trouble with these questions. Okay, so these are going to be figuring out our initial rate by our data. So you can always tell because you're always given data here. So for our first one, let's say we want to figure out N2, because we need to figure out with respect to N2, then we need to figure out O2. So we look where N2 is changing, but O2 isn't changing. So you can see O2 is not changing here. So we're going to use experiment 2 and experiment 3. Right? And in general, you just write the rate law. So rate, this is our rate law as always. It's going to be K times, and specifically, so it's going to be, I'm just going to do the whole thing. It's N2 to the, I don't know, X or M or N or whatever you want to say, and then O2 to the Y. That's our rate law. So we're trying to figure out our X and Y. Well, our O2s are going to be constant. So we're going to ignore that. And so when we write this, we have the rate equals K times N2. So we're just going to use two of these. So for time, I'm just going to do it like this, and for space. So our rate for experiment, I don't know, let's do 2/3. So our rate is 0.04 equals, and the K's are going to cross out, equals K times N2. To the X. Okay, and then it's going to be over, sorry, wrote it backwards. It's 500 equals K times, I'm trying to write extra slow here, 0.04 to the X over 125 equals K. See how these just cross off? So I'm just going to ignore them. Times 0.01 to the X. And then we just put this in our calculator. And what you get here, I'm not sure. I think you get, put this in your calculator, which my calculator is, of course, packed away. Let me see if I can try this on my phone. So 500 divided by 125. 4 equals 0.04 divided by 0.01. 4 to the x. And again, how you do this is you take the log of both sides. So the log of 4 equals x log of 4. Divide, I can't divide this. I'm going to do it over here just really quickly. So the log of 4 equals x log of 4. Divide by log 4, divide by log 4. Right, and we get 1. X equals 1. This crosses off. Okay, so that's the long way. I'm not going to do it the long way. I'm assuming you can do the math after this. And so when you do this, that means that our rate with respect to our N2 is 1. So that's first order for our nitrogen. Okay, so I'm gonna have to erase all this. So now this is what we know now. Our rate equals K N2 to the 1. And we don't write that one, but I'm just saying it's the 1. And O2 we still don't know. Okay, so the next one, I'm going to do this one without all the math. And again, if you need to look at this math more, look at the pre-lab lecture for experiment 10 and look at the second lecture that we did on kinetics. Okay, next one. We need to figure out O2. So we have to look where N2 is the same. So we're going to do experiment 2 and experiment 1. Right, so for this one, we write the same thing. So it's rate. So I'm just going to do, I like doing that one on the top. So it's going to be 707 equals O2 to the Y. And again, you can do this by inspection, by the way. You can't do this one by inspection. The other one you could have done by inspection. I'm just showing you the math part because that's the hardest. And then 500.01 to the Y. Then you put those in your calculator, you do the logs, and this one people had a little bit of trouble with. You end up with 107 divided by 500. So when you end up with this, you end up with Y equals 1/2. So when you finish all that math, you get Y equals 1/2. So, or 0.5. That's what my calculator says, 0.5, close enough. And so this is going to be 0.5, oops, 0.5, or we would write 1. Well, let me write. It's not going to let me write up here. 1/2. Okay, so this means our rate law, I just wrote that on the wrong one. I'm just going to write it down here. Our rate law is this. Rate equals K times N2 to the 1, but we don't usually write the 1, and then O2 to the 1/2. So that means our overall reaction order is 3/2 or 1/2, however you want to say it. So that's our overall. So it's 3/2 overall. It's first order with respect to N2, and it's half order with respect to O2. Now to find K, you just plug in any experiment you want. It doesn't really matter which one you do. I always use the first experiment. And so you just plug in each of these values for K, each of these values for your rate. And then we just, sorry, my dogs. Hold on one second. They're probably just going to keep doing that. So we're just going to ignore my dogs for a second. Okay, so then we just plug in all of this information here for our rate. Hold on one second. They'll stop eventually. All right, so if we do this, we just plug in our rate, 707 meters per second equals K times 0.04 times 0.02 to the 1/2. So we plug all of this in, and let me just put my units in here. I did not mean to erase everything, but I want my units in here so you can see them in the end. So K times 0.04 molar times 0.02 molar to the 1/2, just so you can see how these units work out in the end. And then we plug all of this in, and so we divide by all this here. I'm going to run out of room. 0.04 molar, 0.02 molar to the 1/2. And so when we put that over here, again, you're going to put all this in your calculator, but I'm just setting this up so you can see what happens with our units. They get a little crazy. So when we do this, we end up with 1.2 times 10 to the 5th. And our units are m to the negative 1/2, s to the negative 1. So we can see here, I'm going to try this in a different color. This m is going to cross off with this m, but we still have this s on the bottom, hence to the negative 1, and then the 1/2 on the bottom, hence to the negative 1. So our units are m to the negative 1/2, s to the negative 1, right? Or that is the same thing as 1 over m to the 1/2 s, right? Or some people like it better like this, right? This is the same as that. All right, any questions on this? Again, questions on this one? Someone had a question, why isn't that? Okay, so let me write these units. So this m is going to cross off with this m, because this m is on the top, this one's on the bottom. It leaves this m here on the bottom and this s. So if I rewrite these units with just the units, so we have m over s, that's this one. I'm going to do the other ones in blue. I'm going to do these two in blue. M, that's this m. This is the 1/2. M 1/2. And so you can see that crosses off that. Yeah, the question was does this exponent, hold on, let me just go with yellow. This exponent, yes, does apply to this. So if I distribute this exponent here, it's 0.2 to the 1/2, m to the 1/2, right? So that exponent does distribute to the entire thing. Yes, so I think that was the question. The exponent does absolutely affect the m also. All right, any other questions on this one? Oh, so it says, someone asked, like, if you're doing it the long way, do you always put the bigger one on top? It'll work either way. I just don't like it. It'll work either way. I just always put the bigger one on top because it makes my brain better. It just makes my brain work better. But it'll work either way. But I always like putting the bigger initial rate on the top. That's just the way I always do my problems, but it'll work either way. All right, and again, you can do it by the inspection. So the first one you could kind of do by inspection, but the second one, there's no way. You couldn't have seen that was half order. All right, any other questions on this one? Any other questions? If you have any other questions later, feel free to ask. And again, if you have questions on this type of problem, this is pre-lab experiment 10 lecture, second lecture from our lectures, the second one. Okay, the next thing we're going to look at are the integrated rate laws. Now, this was the third lecture we did. So this is on the third lecture. The stuff from the first lecture, that one's the easiest, so I didn't put any of those questions in here. You should be able to remember those. Those ones are the simplest. Okay, so remember what you're going to be given on your exam. So this is not going to be here. So you're not going to know what the order of the reaction is. I'm also not going to give you these, so you need to make sure you know these. I'm also not going to give you these. Right? So those are not going to be everything else on here. So you will be given these three things. You're not going to need that, and you'll be given these. So all of these will be given to you. So you need to remember which one is which. And so what do you need to remember? You need to remember which ones belong to first order, zero order, first order, second order. Okay. So first order, remember, is always going to be A versus T. Sorry, first order, zero order. First order will be ln of A versus T. Second order will be 1 over A versus T. And someone had a question about the OLI quiz. For the OLI quiz, you just need to make sure if they were just doing A over T, they might have been graphing something else. So if they had a positive slope, they probably weren't graphing A versus T. If they did send me a screenshot of it, but they probably were graphing probably something else, but not A over T, or they were doing T versus A. Okay, so ln over A. Yeah, and it's always, the question was, is this always a negative slope? Yes, yes. If it's zero order, it is always a negative slope here. Okay, so A versus T, 0. ln A is 1. 1 over A is 2. So that's pretty much, so what do I always tell people to remember? This, 0. ln, 1. 1 over 2. Why do I say that? Because look, this is just A's. It's 0. These are ln's. This is the natural log of 2. ln of 2 is just point. These are ln's. These are all 1 overs. So if you just remember ln is first order, 1 over is a second order, regular or just A's are 0 order, then you don't need to memorize which reaction goes to what. You just need to remember which one belongs to 0, first, second. And then the slopes, you do need to remember the slopes. Negative K, K. But you can see that this is a negative slope and the slope is always K. So it has to be the negative of it. It's a negative slope, it has to be the negative of it. This is a positive slope, so it's just the positive of it. The y-intercepts, again, completely correspond to the order. It's just A. It's the ln of A. It's 1 over A, right? And then all your equations, again, work the same way. So you do need to know how to use these equations. Okay, so practice with using these equations. I am not going to make you graph on your exam, nor will you be graphing on your final. You will see something like this. Here is the data, here is the graph, and there is the slope. And the question would be, what is K? Okay, so based on what we just talked about, I'm going to give you a minute and then type what K is in the chat. So I'll give you a couple of minutes for this one, and then we'll go over this together. All right, so I'm seeing a bunch of these now. All right, so we are seeing that this is the natural log, right? When we see natural log, we think first order, right? So when we see natural log, we think first order. So this is a first order reaction. So a question could have been, what's the order of this reaction? That could have been another question. First order, why? That natural log, that's what gives it away. The slope is negative. Whenever there's a negative slope, and this is an integrated rate law, it's always K is always the negative slope. So K is just going to be positive 0.00693. Now, you do have to remember the units of K, right? And this is going to be inverse seconds or 1/S's. So if I go back here, these units of K, you have to remember because you can't see it from, you can, when you actually do the math of it, you can see it, but when we're given a graph, you can't see the units. So you need to remember these units of K. So how did I know that this is S to the -1? I have memorized this. You have to remember that. Again, when you're doing the actual math of it, you don't need to because we can just cross them off and see it. But when you're looking at the graphs, you need to actually see it. You actually need to memorize it to write it down. And there's a supplemental lecture that's literally called Finding the Units of K. That should help you. And that's just, it's like 5 minutes and it's posted right in the experiment 10 module. It's called Finding the Units of K. Okay, so that's our K. That's it for this one. That's all this question had in it. It's just using these integrated rate laws. Okay, so this again is just going over everything we talked about with our integrated rate laws and what makes our linear plots. So 0, first, and second. So this is the same thing as the big graph. I just made it smaller. So remember 0, and I have X's instead of A's here. Everything's just straight. First order, that's where all those LNs come from. Second order is the one that has the 1/overs, right? So just remembering how we do these. Okay, so now let's, again, this is the same thing here. I just kind of made it smaller. All right, let's try a practice question. For the first order decomposition of NO, so I'm telling you it's first order, I want you to calculate the half-life. All right, that's the question. First order decomposition. What is the half-life? Okay, so try this one, and then we're going to go over this together in just a minute. And type your answers in the chat. We'll go over it in just a minute. So I see a few of these. So calculate the half-life for this one. Yes, I see tons of these. Okay, so for a half-life, oops, we're going to do that one in just a second. So we decided this was going to be first order, so we just look it up. So it's ln of 2, or that's 0.693 over K. right? And so this ends up being 0.0124 inverse seconds. And our answer is, yes, 55.9 seconds. Okay, second part, calculate the molarity of NO remaining from 10 molar NO after 100 seconds. All right, this one's a little trickier. So try this one. So we've decided, yes, it is first order. First order. And so we use this for our half-life. And so now we need to use the other equation, which I'm not going to help you with, to calculate the molarity of NO remaining from 10 molar after 100 seconds. All right, try this one, and then we'll go over it together in just a second. All right, seeing a couple of these, a few different answers. Okay, so here's our first one. 55.9 seconds. Our next one, here is the equation we chose to use, first order. And I just rearranged this equation. And I got 2.89. Okay, so I promise I'll come right back here. So what I did was I rearranged this equation. So I rearranged, hold on, let me write the equation for you. ln every time I try to write, it keeps disappearing. ln of A try this again without it disappearing. Negative KT plus ln of A0. ln of A, do it proper, exactly like it is there. Right, so I did was rearrange this equation, right? So if you take the way to get rid of ln is you'd use e to the, so I just took e to the both sides and rearranged and got this equation. Again, however you solve this is fine, and you end up with 2.89 molar. So, all right, any questions on this one? So this is just the application of the integrated rate laws, right? So application of our integrated rate laws. Let's do one more application question of these. I don't know why my slideshow keeps disappearing. Let's do one more. All right, so this one, I want you to calculate the half-life of a second order decomposition of NO2 if K equals that at a particular temperature and the initial concentration is this. Okay, so also, so while you're doing this problem, I want you to notice this. Here, I'm giving you how this one has the units of K here, and it says it's second order. And you see how this one says the units of K here. So if these were questions on your exam, it says first order, it gives you the units of K. So have you ever heard the saying, use the test to take the test? Here, this is saying this is second order and here's the units of K, right? So if a question, and you had to figure out, there was a question on your exam where you needed to figure out the order of the units of K and it was second order, you would be like, oh, I remember seeing a second order and it told me the units of K. Now, I'm not saying that will be on your test, but I'm saying you should definitely use the test to take the test. So always kind of look through it for little hints. Okay, so try this one. Shouldn't take you very long. I'll go through this. We'll go over this one in just like a minute. This one's back. This one's pretty fast. Okay, see a few of these up here. Yep. Oops. This one down for you. Yep, so 2.5. Half-life is 1 over, because it's second order. So it's 1 over K. And so it's just going to be 1 over 0.544. And this is m-1, s-1 times, oops, I forgot this part, times NO2 times our concentration of NO2, which is 0.01 molar, units, and we end up with 184 seconds. Okay, so those are both applications of our integrated rate laws. So typical questions you get with integrated rate laws. Why this slideshow keeps changing, I don't know. Any questions on any of those so far? If you come up with them later, feel free to ask at any time. Okay, so now let's look at mechanisms. So remember, mechanisms are looking at the elementary steps, right? And the elementary steps are when the molecules actually hit each other. So most of the reactions we've seen are just the summary, right? It's the overall reaction, but there's actually a series of small steps, right? If it's one molecule hitting one molecule, we call it unimolecular. 2 molecules, bi, 3, tri, but 3 like never actually really happens, right? And remember, when we have these elementary steps, we can deduce the rate law from these elementary steps. So the mechanisms is the series of these elementary steps. And when we add them all up, we get the balanced chemical reaction. So remember when you learned about balancing chemical reactions in like Chem 209, where those actually come from is the elementary steps. That's what actually adds to the balanced chemical reaction. Okay, the rate determining step, this is the slowest step. So the reactants and the reactions rate are always in the rate law are always based on the rate determining step. That's what determines the rate law for the overall reaction, is that rate determining step. Okay, so I'm going to show you one, and then you're going to do one. So here's this one. So here's what's going to be. So if this was an exam question, this would be given to you, this part. So it says the reaction occurs in a 3-step mechanism. Okay, so what do you need to do? So this one would ask you to prove the mechanism, right? So prove the mechanism, or it might say, what's the overall rate law for this step? What's the overall rate law? Okay, so what do you, these are, they have to be given to you, or at least this one will have to be given to you, and it'll say slow. Slow means it is the rate determining step. And so this means our rate law is, I'll just write it here because I have it, that times that. This is our overall rate law. But now we need to prove this. And the question is, what's the rate law for the overall reaction? Do you see how these do not match? This is our rate law for the reaction. And yes, no. There's no Cl here, it's Cl2. We have to get rid of this, right? So we have to get rid of the Cl. We can't have this be our overall rate law because it doesn't match our overall reaction. So this Cl must be an intermediate, and we got to get rid of it. How do we do that? Algebra. Okay, so remember this. If there's a rate determining step, the one before it goes backwards and forwards. So that means the rate going forwards equals the rate going backwards. And so we can say that K1 times Cl2 equals K-1 times Cl squared. This means this. Again, because it's going forwards and backwards. Okay. So then we can see, here's our Cl. So we need to get rid of the Cl. So we need to find something to substitute the Cl. Well, we can do that from right here. So if I solve for Cl, and there's a lot of K's floating around here. In the end, we just write all the K's together. So I'll keep our K. So if I I'm just gonna ignore these K's, because in the end, we just have a big K. Actually, you know what, for being thorough, I will not ignore the K's. So if I did put this K on the other side, right? And then I need to get rid of this. I'm going to take everything to the 1/2, right? If I raise this to the 1/2, it'll get rid of this. So that means I have to raise everything over here to the 1/2. So I end up with K1 times Cl2 to the 1/2 over K-1 to the 1/2 equals Cl. Again, I'm trying to substitute the Cl here. Oops. All right. My computer. So Cl equals this. So therefore, I can plug this in here. So my rate equals K2. Now I'm just going to put it all together. Times, so I'm just bringing this down, CHCl3. And now I'm going to bring this down because this is Cl. K1 to the 1/2, CL2 to the 1/2 over K negative 1 to the 1/2. We combine all the K's and we just say rate equals K, overall K, times CHCl3 times CL2 the 1/2. So because we take all of these K's and we just combine them and we call it K overall, that's why I was saying in this part, you don't have to do the K's where you can just ignore the K's here because we're going to combine them all into big K anyway. So you don't necessarily need to keep those when you're doing your algebra. You can feel free to just ignore the K's when you're doing this. All right, so this would be our overall rate law for our reaction. So the question is, what's the overall rate law for the reaction? This is it. How do we know it's true? Reactant, 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 right? And then if we also, another way, they have to add together. So if we add all of these together, you can see we need to cross off any intermediates. So this goes away, this goes away, this stays. 2Cl, Cl, Cl. And so we have, there's a reactant, here's a reactant, there's a reactant, there's a reactant. Yes, these three all add to our overall reaction. And in our rate law, we have only reactants of our overall rate. Okay, questions on this one? Because you're going to try one of these on your own now. Okay, let's try one. It's just the same thing I just did. Okay, so here's what's going to be given. This, 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 this. And I want to know, what is the overall rate law for this reaction? The question is, what is the overall rate law for this reaction? Okay, I'm going to give you a few minutes on this one. Okay, what's the overall overall rate law for this reaction? Okay, so try this. You can type this in the chat. You can type this in the chat. I'll give you a couple minutes and we'll do this one together in just a few minutes. Okay, so I'm seeing a few of these and people are getting them correct. Okay, so our rate determining step is this one right here. And so we have to prove this mechanism. We have to get rid of this. We have to figure out the overall rate. So this cannot be yes. Oh, it has to be with respect to I2. So we need to substitute and get rid of this I. Again, how to do it? Algebra. Okay, so because this one is fast, we can go forwards and backwards. And so again, when we do that, that means that H2 times I equals H2. I'm totally going to not even talk about the K's right now. Right? And so now, so those are equal to each other. So I can, oh, whoops, I did not mean that. This is H2I, not okay. Because this is I, not okay. Neither of those are okay. Okay, so that means we need to get rid of both of those. We need to get rid of both the H2I and the I. Okay, so how can we do that? Well, I see an H2 here, so we can solve for our H2. So when we do that, let's look at this one also. Let's just do this one at the same time. I2 equals I squared, right? Again, why? So why can I do this? Because of these. So that's why I can say they are equal to each other. And so we can plug in our I's. Remember this. So what did I do here? I did this. By the way, there's so many different ways you could have done this. I squared is the same thing as I times I. That was my little rearrangement here. K1, I squared over I, right? That's just me rearranging the first one here. And then we just plug all these in and we get H2 times I2, right? So again, however you did solve this is fine. There's a few different ways you could have proven this mechanism. You could have started with one or the other, but basically what you do is you use your algebra, solve for this, and then plug it in. So we solve for our H2I, right? H2I equals these two. So I plugged that in here. There's my H2I. And then I've got another I here. So then I rearranged our second one, solved for I2, and plug that in here. And again, it's a couple different ways you could have done this. That's just the way that I did that. That's not squared. I'm trying to figure out this question here. So this one here is this. Over here, I've got an I left. So I solved for my I. When I solved my I at I2. So I'm not sure what the question is on this one. Any other questions? Oops, you're right. I meant this here. And then I squared is I2. I think that was the question. And again, you can ignore all the K's when you're doing these because in the end, you just write this big K. So you don't need to do all these K's. Okay, so that's proving the mechanism. The last thing we're going to talk about quickly is activation energy. This was the fourth lecture. So a little bit of the end of the third, beginning of the fourth lecture. So remember, what is activation energy? The minimum energy needed for the molecules to have an effective collision. And so we have our reactants, our products. And so there's two different types you might see. You might see this one as an exothermic which is a negative delta H. This one has an endothermic, which has a positive delta H. The only difference is, again, for our reactants and our products, you can see that our products have less energy than our reactants, and that's what we call exothermic because heat exited the equation. This one is an endothermic, which has a positive delta H, meaning our products have more energy in their reactants. So this is a positive delta H. You might see either of these, negative delta H. You might see either of these reaction profiles. So these are both called reaction profiles. The activation energy is just the distance from the reactants to the top of, again, this is our activated complex. That's the symbol for our activated complex. Again, our activation energy is our reactants to the top of our activated complex. That is our activation energy. And you can see this one has a small activation energy, this one has a large activation energy. But these are both reaction profiles. Okay, so again, this thing on the top is our activated complex. So let's look first if we're going forward. So if we're going forwards, so we're going to go forwards in our reaction. Our activation energy is right here. EA. But what if we go backwards? If we go backwards, then it's different. Then this becomes our products, these become our reactants, and now our activation energy is much larger. So if we go forward, so this reaction happens faster in the forward direction and slower in the reverse. Now, why? If we're going forwards, our activation energy is smaller, right? Smaller activation energy, faster reaction. If we're going backwards, so that makes this our reactants and these our products, then our activation energy is much larger. Because remember, the activation energy is always the distance from the reactants to the top of that activated complex right here. And so it's going to be slower if we're going backwards because the activation energy is bigger. So you can tell how fast a reaction is by the size of the activation energy. So you can actually see this going forward and reverse in one single reaction profile. Okay, so remember this highest possible state, that's the transition state of the activated complex. And again, this is the little symbol we use for the activated complex. Remember, it's the molecules that are colliding with each other. And this is when bonds are both being broken and formed at the same time. It's highly, highly unstable, this activated complex. Okay, so again, the activated complex is going to be a single unit when we're breaking new bonds and forming. So we're both breaking and forming at the same time. That is our activated complex, very unstable. Okay, so calculating our activation energy. Remember, our activation energy depends on the concentration of the reactant and the temperature. We did both of those in our lab. So these are going to be on a microscopic scale due to both the collision frequency and the fraction of the molecules that have the proper orientation and enough energy, right? So how often they collide, the orientation and the energy, all of those things. And those are all in our activation energy. So remember, Arrhenius figured this out. Z is the collision frequency, P is the fraction, and then this is our activation energy, right? And so remember our Z and P, and again, this is the fourth lecture, the beginning of the fourth lecture, if you're confused about this. This A has both of these pieces in it. So the collision frequency, how often they collide, and how often they collide with the proper orientation are all included in this A, and we call this the pre-exponential factor. The second factor is this, and this is we call the exponential factor. This is the fraction of collisions with enough activation energy to get over. So this means they have enough energy to get over the hump. That's this piece right here. This A is the number of molecules that are trying to get up. The exponential factor is the one have enough energy to get over. So again, A we call the pre-exponential factor, and EA is the activation energy. So here might be a typical question you're going to see. Again, I'm not going to make you graph. I might have you use the 2-point form, but again, if you're going to use the 2-point form, I will give you that equation. But you might see something like this. So here's the data. So this is just like we did in our lab. Here's the data. And then here's the graph when they graphed the data. And then they tell you here is the slope and here's the y-intercept. So all of this would have to be given to you. And then they give you the reaction and they want to know the activation energy and the frequency factor for this equation. Okay, so I'm going to give you a minute to try this one, and then we're going to go over it in about 2 minutes. So we want to know both the activation energy and the frequency factor for this reaction. So try this, and then we'll go over it in just a minute. And you know what? I'm going to help you with these equations because you're going to be searching for them. So I'm just going to help you with these equations, but I'm not going to give you these equations on your exam. So you need to know this. So in here, the slope is going to be negative EA over R, and A, or the y-intercept is ln of A. Okay, so I'm giving you this. And I will give you this. R is 8.314 joules per mole. Okay, this will be given to you. Okay, so now with that data, I will not be giving you these, so you need to remember this. We'll be giving you that. Okay, so now try this one and then type it in the chat. We'll go over it in just a minute. All right, so I'm seeing these. So our slope is again going to be, so EA, so I'm just going to rearrange this. So EA equals negative slope times R. So we just plug this in. So negative 1590 K times our R, which is 8.314 joules per mole K. K crosses off. And our activation energy ends up being 1.32 times 10 to the 4th joules per mole, which is the same thing as 13.2 kilojoules per mole. Yes, often this is activation energy is almost always in kilojoules per mole, so you need to remember that there are 1,000 joules in 1 kilojoule. Put that one in your brain, probably gonna need it. Okay, for our A, we rearrange that. So A just equals E to the 28th. So when you do this, we get 1.45, I think, 1.4544. If we do our sig figs, I guess it would just be 1.4 times 10 to the 12th. And that's what we get for our pre-exponential factor. So this would be two things you would do with your activation energy. Remember, there's the 2-point form also. I didn't give you a practice one with that one. We did that one in lecture a few times. So I just wanted to go over those. But again, you would be given that equation in the 2-point form. Okay, just lastly, again, what do catalysts do? They decrease the activation energy, and they decrease the activation energy in the forward reaction and the reverse reaction, right? So when we do this, a catalyst decreases our activation energy, right? And it decreases it going this way forward, but it also decreases it that way. So it makes the reaction go forward quicker in the forward direction and the reverse direction. It does not change the concentration of our equilibrium. Now remember, there's homogeneous and heterogeneous catalysts. I wanted to show you a heterogeneous catalyst. So this is like a metal surface and these are gases. So this is a solid and these are gases here. And so you can see it's a catalyst, so they react on the surface, and that would be a heterogeneous catalyst versus a homogeneous catalyst. Remember, they're in the same phase. So just different types of catalysts. Okay,